other questions?
Yeah. So this debrane tension calculation, I mean, if we don't know the annulus partition function,
Yes.
it seems like we can still do it, but like the only thing you used was that the leading power of that number times t to the beta.
Yeah.
Is that much information?
You need to calculate something in which involves the disk, right?
Yeah.
Yeah. So I mean, annulus hard point function should also do.
Okay, I mean, but that will be like even more.
Yeah. Yeah.
But like if I just maybe knowing the full annulus partition function is an overkill. Like
Yeah, you only need the in a certain limit.
In a certain limit.
Yeah. But the point is, if you are calculating it from the open string perspective, right? Then from the open string perspective, you need the know the expansion for small t. Sorry, for large t, because you have e to the minus t times L0, right?
Like the low mass modes.
Low mass modes. Yeah, large t is something that you know, right? But what you need is the t goes to 0 limit of the partition function, right? So from that perspective, you really need the whole information, because what you are doing essentially is that you are looking at the massless closed string exchange, right? But the massless closed string exchange is in the dual channel, right?
Yeah.
Okay, that corresponds to highly excited open string states,
right,
propagating in the loop.
Yeah, last class we did this deep branes, two deep branes and the interaction.
Yes.
One deep brane, how can I calculate the back reaction on the geometry?
Yeah, we'll do it today. Back reaction, of course, one D brane will not, I mean, because you are doing perturbation expansion, right? One D brane will not have very much back reaction, because at weak coupling, right, D brane doesn't back react very much. You need a lot of D branes to actually have it back react. Any other question? Okay, so last time we calculated the tension of the D brane by looking at two separated D branes, right? You said that it's like two D branes separated by distance r, and you want to calculate the energy, interaction energy, and we calculated in two different ways, and that's how we got the result. But this one is not going to work for space filling branes, D9 brane, for example, right? Because D9 brane fills the whole space, so there is no transverse direction in which you can separate them. Okay? So now the question will be, how do we go about calculating the tension of a D9 brane, right? Or any other space filling brane, for example. Okay, so this is what I'm going to describe today. Okay, and it will be some variation of what we did last time. Okay, but it needs a little bit better understanding of what's happening on the worldsheet front.
Space filling brane doesn't back react.
Space filling brane will back react. But space filling brane, once you have a space filling brane, that basically means that that's not a consistent configuration, right? So you have to cancel the charges. So like, for example, if you take type 2B string theory, it has a D9 brane, right? But if you actually have a D9 brane in the system, it's not a consistent background. Because it will back react. I mean, it has a cosmological constant, first of all, right? But more severe problem is that it has Raman-Raman charge, right?
What is the issue?
Raman-Raman charge is like if you have a sphere, right? Suppose our space-time was our spatial directions are all compact.
Then total charge will vanish.
Total charge will vanish, right? So this is exactly the analog of that, right? Here there is a transverse direction, right? So what the three-dimensional space is like 0 dimension, right? And you have a total charge, right? So that flux has nowhere to leak, right? So that's why it's not consistent, right? So having a Raman-Raman charged object, space filling, right, is like having a point charge on a compact space. Okay, this is important because this means that you cannot have D9 brane, but if you have something else to cancel the charge, then you can have it, right? And that's what we'll discuss today. Okay, so you want to calculate the tensor of a D9 brane. And our starting point will be the same. Okay, the effective action, there's a T sitting in front. Because if you have something like this, you can see here that if you take the equation of motion for C, right, you just get a constant, right? So equation of motion can never be satisfied. Okay, that's the problem. But let's ignore this for now. Okay, and let's suppose you have an interaction like this. Then, by following the same procedure that we described last time, okay, we can calculate the correction to the energy. So can calculate correction to the energy. This is the interaction energy, or to the action, self-interaction, yeah, due to self-interaction. Okay, so instead of having two separated debranes, we just have one debrane and are trying to calculate the correction due to self-interaction. Okay. And this will have the structure, there is a T square. Okay. Then some constant, let me call this C1, just not to confuse with various constants we introduced last time. Okay. And then we have D10y, D10y prime, GYY prime. Yeah, this is the Green's function of massless particle in 10 dimensions. Okay, so you have this is the interaction term. Now this I'm going to write as integral d10k over 2 pi to the 10 Yeah, it will diverge. So you have to deal with infinite quantities here. Okay, but we will try to see that there is have to make sense of this divergence. C1 comes basically because the exchange is not just metric. There is also a dilaton, right? Metric has various polarizations, right? So if it was just a massless scalar, then this will be the result, maybe a factor of half or something. Right? But because you have various components of the metric, the dilaton, right, they couple differently. So basically, the one-point function is what we need, right? One-point function of h mu nu and phi, right? Because we don't need the full effective action. I have written this. Sorry, there is e to the minus phi also, which I forgot. And there is the full effective action, you know, right? But the part that we need is a linear part, right? Because what you are doing is that you are coupling it to linear coupling to the fields, and then you are basically looking at the exchange, right? The field gets emitted and comes back. Is clear? So we are basically in terms of Feynman diagram, we are calculating Feynman diagrams like this, right? Where this is the linear coupling. Coupling of h mu nu and phi and C. And that's what is getting exchanged between these two. That's what is propagating here. Yeah, so that is of course a purely closed string effect, right? This is on top of that. If you have a space filling brane, right, you also have it's emitted from a D9 brane and coming back to the same D9 brane. It's clear. Imagine that you have a linear term. This gives a linear term in the action, right? So linear term means what? The Feynman diagrams have one-point vortex, right? So once you have one-point vortex, you can use it as many times as you like, right? In any Feynman diagram. And here I am just using it in this Feynman diagram, right? Two one-point vortex, right, connected by a propagator.
What happened to diagrams that start at one point and end at? That is, you are saying only from close.
That is closed string, yeah, because they are constantly periodic. This is actually, okay, yeah, this is because this doesn't have to end at the same point because it's y and y prime, right? If you force periodicity, that is like closed string, right? If it has to end, this includes points where y prime is equal to y, right? Because you are integrating over y and y prime anyway, right? But the forced equality of y equal to y prime will be only for closed strings.
You are saying that, I mean, that C1 is there because we have three fields.
Exactly, yeah, and there may be factors of half, etc.
But shouldn't there be a matrix? I mean,
Yeah, there's a matrix. That matrix I'm assuming that you have evaluated. See, because everything is proportional to T, right? So this matrix will be sandwiched between two column vectors, right? So that result is what I'm calling C1. Right? Because you are right, there may be mixing between the H, mu, nu, and phi, for example, right?
I guess since all three are massless, so
Exactly, all three are massless, so that's why this is the same massless Green's function, right? And then we just use a matrix to calculate this. And again, if we include the contribution from Ramon and NS, the result cancels. So you keep in mind that this is only contribution from either the Ramon or NS, because you have to compare separately. Okay, this is the same feature that we saw last time, right? For separated difference or coincident difference, right? The Ramon, for supersymmetric ones, Ramon and NS exchange contribution cancels. Okay, so you are looking at it things separately.
what does that mean here?
That here in this,
Separating Ramon.
that in this there is a Ramon exchange and NS exchange, right? We calculate it separately, right? And this is the contribution from one of them. Otherwise, C1 will be 0. Right?
Like at the level of, I mean, this action, but Ramon.
Oh, because this is Ramon, right? So this is Ramon one-point function, right? And this gives you NS one-point function, right? Kinetic term don't mix Ramon and NS, right? So this diagram will have NS exchange and RR exchange, right? So the statement is that if you add the two, the result is 0. Okay? You don't add. Right? That's why when you compare the open string, you have to separately look at the Ramon and NS contribution, right? As we did last time. Is this clear? Right? So you don't add things here, right? Keep NS and RR separate. Okay, now this of course is infinite, but what we will do is we will try to rewrite this as integral ds e to the power minus sk square. Okay, 1 over k square, we are going to regulate using it, the Swinger parameter. And then we can do the y prime integral d then y prime e to the I k dot y minus y prime is basically setting delta n of k e to the I k dot y, but e to the I k dot y is irrelevant now because k has been set equal to 0, right? So this we can forget. Is this clear? Just I am doing the y prime integral to this e to the I k dot y minus y prime, and this is basically saying that this exchange, right, this diagram that we drew, right, this exchange will be happening only in the zero momentum sector. Okay, and that basically follows from translation invariance because this D9 brane is space filling, right? So there is translation invariance on a D9 brane, so it cannot violate momentum conservation, right? So only zero momentum closed strings can emerge out of it. This is like if you have a scalar field phi and if you want to write an action, right? Suppose you want to add a term in the action which has a linear term, right? You will let integral d10x phi x, right? Okay, you cannot write just phi x because that will break translation invariance. Right? Integral d10 x phi x, but in the momentum space, that is like phi at 0. 0 momentum, right? Okay, so only 0 momentum can have tadpole, right? If you want to maintain translation invariance. Right? And that's what this is reflecting, that there is a delta k. Okay? But using this, we can now write this as p square c1, that is 2 pi to the 10. Okay, so p square c1, then volume of space-time, which is coming from the y integral, because everything becomes y independent, right? Because k has been set equal to 0. So this is from y integral. And integral 0 to infinity ds. Pardon? Moment, because using the delta function, I set k equal to 0. Right? The momentum integral is gone, k has been set equal to 0, so you are just left with this integral over here. Okay. Now this of course is divergent. Okay. But you understand what the origin of the divergence is, right? Because if you look at where S is appearing, right? This was the way S was appearing. Okay. For non-zero k square, this is perfectly finite. Okay. But k is being forced to be 0 by momentum conservation, and that's where the divergence is coming. Okay, because this is like 1 over 0. Okay. This is giving something like 1 over 0. Okay. Nevertheless, we will see that this expression will be useful. Yeah, full volume. So in this case, D9 brane world volume is a full space-time volume. Right? This is a squeeze. So this comes from y integrals, full space-time volume. Yeah, that's also divergent, but that divergence is okay because I mean the action, you are calculating the action, right? Translation invariant system. So there will of course be a factor of volume. Okay, so this is not a surprise. This is the one which is something that you have to deal with. Okay. So at the end, right, once you include all the contributions, it better be that this divergence goes away. Right? And that is a statement that this tadpole, we cannot let it remain. We have to cancel the tadpole. Okay, this 1-point function.
And then add both NS and RR contribution,
then that term will be 0, right? But then when you include scattering amplitudes, right, those will not be 0, right? If you think in the Feynman diagrams, right? Imagine that you have a complicated Feynman diagram. Okay, you can have diagrams like this. Okay, now here the NS and RR may couple differently to this Feynman diagram, right? So then it is no longer guaranteed that the result will be 0. Okay, so it is true that if you just are interested in the cylinder amplitude or annulus amplitude, the result will be 0. But in other amplitudes, it will show up. This divergence will show up.
but that also depends on how like it couples with NS and RR.
Exactly. But certainly you can cook up systems which couple differently to NS and RR fields. Right? In fact, as we discussed, that the fundamental strings don't act as source of RR field, right? Because they only couple to field strength. Right? If they couple to field strength, then it's okay because then there is an extra factor of k that is coming from here. Right? But NSNS fields, NSNS particles, right, directly coupled to the NSNS fields, right? The energy and momentum, there are many things which carry energy and momentum. Okay? So those will have non-zero contribution here. Right? And that will make it vanish. That will make it diverge.
Can you tell that again? What was that related to how was that related to the tadpole?
This one?
The linear term in phi you were saying. Oh, like the delta k you got.
Yeah. So this, why this is related to tadpole? Yeah, so this came from this integral, right? And that reason that we are getting divergence is because k is forced to be 0, right? Now, the diagram that you are calculating is this one, right? The coefficient has this t square c1, right? So this is the diagram that we are calculating, right? And we have to evaluate 1 over 0. That's why the divergence is coming, right? Okay. But if this 1-point function had been 0, then this problem will not be there. Because it will be 0 times 1, this, right? See, the problem comes because there is a 1-point function, right? And then you have the exchange, right? So if this part was 0, say, look at this diagram, right? If this was 0, then this diagram wouldn't exist, right?
Wouldn't exist.
Or would exist, but it will be 0, right? There's no linear term, right? So the problem is coming because there's a linear term involving massless fields.
Okay, that I can see from that.
That you can see from there, right? And basically this 1 over k square is essentially representation of that. Is clear? This is a Feynman diagramic way of writing what I have written here, this one.
So, I mean, can I summarize it like this, that I have a linear term of massless field that is causing this?
That is causing the problem, right? And you can directly see why, right? Because if you write it in the momentum space, right? The 1 over k square is this propagator over here, right? And then the integrals, the sources, okay, when you convert to the momentum space, they are having a delta function, right? Which basically is saying that this particle is forced to carry 0 momentum, right? And that's the 1 over 0 that we are encountering here.
If it had been massive, we wouldn't have.
Yeah, if it had been massive, this problem wouldn't be there, right? So this problem comes only for the massless sector, right? So that in other words, this divergence that you see for large S, right, is coming purely from the massless sector, right? Even if you include the effect of massive exchange, right, the coefficient of the divergent term will not change, right? Because there will be 1 over k square plus m square, right? So there will still be 1 over minus s times m square, okay, and that will converge. That integral will converge. Is clear? So we are now going to compare this with the open string channel. So in the open string channel, okay, as we saw last time, okay, we have integral dt over 2t. Here in this, in fact, there is only one kind of open strings, starting and ending on the same d brane. So dt over 2t, some function of t. Last time we also had this factor of e to the minus t times, I think, r square over alpha prime times 4 pi square, something like this, right? Okay, basically it came from minus this part, this whole thing came from the e to the minus t L0 term.
This is when you add both open and closed.
This is, no, not both open and closed. But this you have to take super trace, yeah, but not closed. All in the open string sector. Right? This is from the trace of open, right? Because look at this diagram. Right? This is a trace, okay? Because this is an open string, right? And that is going around in the loop, right? That's why it's a trace. Right? So it's all from open string, right? But there can be bosons and formulas because there are host fields, right? The host fields can produce bosons and formulas. So this is basically trace of e to the minus TL0 times B0 C0, right? Something like this. This is a projection, right? Into the B0 equal to 0 state, or equivalently you can think of this as the the insertion that soak up the 0 modes. Okay, now the difference here is that this term is not there. Right? Today we don't have this term. Okay, and last time also there was a factor of 2 because there are open strings going from the first to the second and second to the first, right? So that factor of 2, that's also not there. Otherwise, this is the same expression that we had found last time. Okay, so you don't have the option of taking large R. Okay, but let's just remember that we found that for large R, the contribution comes from small t. Okay, so that's the only thing that we want to remember now. And we will see that the same thing will happen now.
Because it's space filling, that's why. Because it's space filling.
Because it's space filling, but you could also repeat the same analysis for non-space filling branes, single D brane, right? Whatever calculation I'm describing today, right? You can also apply it on a non-space filling brane to calculate its
But here
tension.
necessary because there is no R because we don't have it.
Yeah. So for space non-filling branes, we have the option of using this.
We have
right?
the option of using it and saying that we are working with a single one.
Well, if you are using the R, right, then you have 2 branes, right?
Yeah,
But I'm saying that that you are we have the option of using today's discussion, right, by using a single brane
This means that we are studying open spectrum
on a single D brane. Exactly, right? Whether it's space filling or not, it doesn't matter, right? Open string on a single brane. So this trace, this includes the momentum integration, open string momentum integration. Okay, so let's look at the geometry here. So this length is pi. This is the open string length. Okay, sigma we take from 0 to pi. And this is what we are calling T. This whole circumference is T because it's propagating over the proper time T, right? Because before you take the trace. Okay, so this is T. Is clear? This is pi. Now we want to reinterpret this as a closed string exchange. Okay? And that we can do because we are allowed to scale. Okay, so we scale by 2 pi by t. Conformal invariance allows us to do that. So this becomes this we want to make 2 pi. And this one now becomes 2 pi square by t. Because we are multiplying pi by 2 pi by t. Is clear? So let's call this t tilde. So now we are going to interpret this as a closed string propagating in this channel. Okay. So we expect a contribution of the form integral dt tilde e to the power with some matrix element. Let's call it A. We don't need to know what this matrix element is, but let me just for single, because you are considering the same D brane, A and B are in fact the same state, right? But it doesn't matter. Okay, some state here, some state there. This is A, this is B. Okay, you can do this also for the separate D branes. Then the B and A will be different states because B will be shifted, right, compared to A. But it's given by something like this. Okay. And this L0 plus L0 tilde will be e to the minus t tilde times alpha prime k square by 2 plus other things. Is clear? Now you see that by this relation, small t means large t tilde, right? Okay, so the earlier we are getting contribution from small t, but in the t tilde language, it corresponds to large t tilde. Okay. And we can also see why large T tilde is relevant, because if you look at this expression over here, right, then in the large T tilde limit, right, the massive state contributions will go away because there will be an exponential suppression to the massive state contribution. Okay.
Those are oscillator.
Oscillators, exactly. Okay. So the massive state contribution will go away, right, and you will be left with essentially massless state contribution. Right. So that's what physically that's the reason why we had to look at small t. Right. Okay. Here we learned that it's small t because R was large. Okay. But the physically we can also see that that can also be seen from this picture. Is clear? So now let's compare this with this. Here you have an integral ds e to the minus s k square. Right? The k square coefficient here was s, and the k square coefficient, this is now the closed string channel. This is the momentum that the closed string is carrying, right? Here the k square coefficient is alpha prime t over 2, alpha prime t tilde over 2. Okay? So you identify this as s. Is this clear? Right? So you identify this as s, even though in this, for this particular problem, k square will be 0. Okay. Nevertheless, for arbitrary sources, right? I mean, suppose this analysis is valid for arbitrary a and b. Okay. So it doesn't matter what a and b are, right? There will be a contribution of this kind, right? And then there is details of what the matrix element is, right? And for space filling branes, this matrix element is what sets k equal to 0. Okay. But we can identify the relation between t tilde and s in a manner that's independent of what we have put for a and b. Okay, and that's the insight you are going to use, right? So t tilde and s are related by this formula. Is this clear? So now we are going to rewrite this as integral. So okay, let me write the relation between t and t tilde. So t was 2 pi square over t tilde. And that now gives a form as 2 pi square times 2 over 2 alpha prime s, which is basically pi square alpha prime over s. Is clear? I wrote the final relation between t tilde, t and s using this. Okay. So I write this now as dt over 2t will be minus ds over 2s, right? Because t is proportional to 1 over s. Okay. Constants will cancel. Okay. And you have f naught of pi square alpha prime by s. Is clear? Small t corresponds to large s. And now the point is that this f naught is of course something in that you know, right? Because f naught you calculate from the open string spectrum. Okay, so f naught is known. Okay. So now you compare with this. Okay, here. So by comparing with this, we learned that t square C1 V parallel. In fact, there is also a V parallel here, which I should have written. Because this F naught, right, includes a V parallel. Okay, doesn't matter. F naught includes a V parallel. So this is equal to limit s goes to infinity.
No, I guess you said it last time.
this trace sort of includes the momentum.
Momentum, exactly. Trace includes the momentum integration, right? So trace includes V times integral d10 k over 2 pi to d10, right? This is k for the open string, right? Not for the k for the closed string, right? So for the open string, there is a restriction on k, right? You have to integrate over k, and that's so the V comes from there, and this f naught, right, includes the result of integrating out that open string momentum. Okay, because from the open string channel, right, it's there like a d10k and e to the minus a k square, right? Because e to the minus t L naught will info, sorry, minus t k square, right? So d10k to the minus t k square you can do, right? And you just get some power of t. Okay, so you are assuming that all those have been done, right? So this f naught of t includes that power of t also, right? Whatever comes from the momentum integral. So we're comparing this, we get this is ds over 2s f naught of pi square alpha prime by s okay, because only the large s you can compare, right? Because for finite s there will also be a massive state contribution, as you learned, right? So only the large s is what you can compare between the two sides, right? So as long as you know f naught of t exactly, you can calculate the t goes to 0 behavior of this. That determines the large s behavior. Right? That's why typically these are modular functions, and you calculate for a modular function, you can calculate the zero momentum behavior where the argument goes to 0 by modular transformation, right? And that relates it to the argument s going to infinity. Okay, otherwise, if we just knew it as a sum, okay, it will be very difficult to extract the small t behavior, right? Whereas in small t behavior, every open string contributes, right? Because it's like e to the minus t L naught. Okay, so it's important that you know what this function is, right? And in any given problem, this function in principle is known completely.
What exactly happened? I mean, we got an integral over 0 to infinity ds that was
Divergent.
But what was that?
Yeah, so here also it will diverge from s goes to infinity limit. If it doesn't diverge, you have to conclude that t is 0. Right? So as long as t is non-zero, this will diverge. Right? And you are looking at the s goes to infinity limit of the integral and comparing with that one. Is this clear? Right? So this way you can calculate the tension of the brane without having to separate them. Okay, but you can also verify easily that this gives exactly the same result, right? Because if we have an option of separating them, right? For example, when the transverse, when the brane is not space filling, okay, you can check that the earlier method and this method gives the same result.
For this I can use for the two parallel thing also. I only take one approach.
Or you can take the whole thing also. Yeah, you can do this for two parallel thing. Yeah, you can do for a single one, right? Then the other one has no role to play. So for two parallel things, you have a choice of using either the force, right, where you have used this formula and look at the R goes to infinity behavior, right? Or you just calculate this, use this method, right? And it's more or less clear why they should be related, because here also for R goes to infinity, we saw that the t goes to 0 limit, that the behavior is dominated by q, t goes to 0 limit, right? And here also we see that large s means small t. Okay, so it's not surprising that the two things give the same result. It basically both method depends on the t goes to 0 limit of this function. Are there questions? Okay, so this is as much as I'll say about D-brane tension. So in the rest of the lecture, I'll be considering unoriented strings. Okay, and we will see that this tension calculation will come back at the end. Both have. This also has V. F naught has a hidden V parallel because of the momentum integral. Right? F naught has a trace over the all open strings, right? So there's a V parallel times D4, D10K over 2 pi to D10. So V parallel just cancels out both on both sides.
Can I see from this calculation why the instant on effect should be suppressed by e to the minus t tension?
Not from this calculation. This will tell you what the de-instant action is, right? And then you have to use the insight. So when you are using this, so this means that there is a finite action saddle point, right? And now when you use that saddle point,
Because V parallel is not there. What exactly?
yeah, V parallel is not there. For de-instant on V parallel is not there.
That's why I have a finite.
Yeah, that's why you know there is a finite action, right? And so then you can use it as a saddle point of the path integral and calculate its contribution.
But that will require me to do what exactly?
This action gives you this calculates the tension, right? Which is the action for the instant on, right? And now we'll basically use the same path integral, same worldsheet rules.
But there is no world volume, like there is no world volume, like there is no integral.
There is no integral of what?
Like if I think of the world volume of the brane.
World volume of the brane, there is no integral.
Yeah.
But the worldsheet is still there, right? You know, use the standard worldsheet method, right? Imagine that there is a d-instant on sitting in space-time, right? You want to calculate its contribution to the amplitude. You have e to the minus 1 over gs, right? That you have to put in because that is the action of the d-instant on, right? So that's the weight factor, right? Because every saddle will have a weight factor given by the e to the minus action. And then you calculate the scattering amplitude in the presence of the d-instant on.
Okay.
Right? So that's the procedure. And the point is that the instant on, normally if you have instant on, you are supposed to integrate over the location of the instant on. But that is part of the worldsheet procedure, right? I mean, the worldsheet already knows about it. So you don't put that integration explicitly. Right? The fact that the d-instant on position has to be integrated, because the d-instant on position is like one of the open string modes, right? And the worldsheet is automatically including fluctuations over the open string modes. Right? So it will already know that you have to integrate over d-instant on position.
Like, okay, yeah.
So you take the d-instant at a fixed position and then do the standard worldsheet value.
Like it's part of the, I can say, open string modulation.
Exactly. It's part of the open string
If I
modulation.
consider all possible Riemann surfaces with boundaries.
Yeah.
The moduli will be like where the instant on rotation.
Yeah, but that's something that you don't integrate separately because open string fluctuations already include the motion of the d-brane.
Yeah.
Of the d-instant on, right?
But separately we do that.
No, but then you have to remove those open string zero mode integrals. Only then you can do the integral over the d-instant on position. You cannot do the integral without removing the zero mode contribution.
Okay. Yeah, maybe we can discuss.
Okay. Okay, so unoriented strings. Okay, this is something in fact we had discussed for bosonic string case also. So we define omega as a worldsheet parity transformation. That takes sigma to pi, sigma to minus sigma for closed string. And sigma to pi minus sigma for open string. Okay. And for open string, right, you also have to specify if there are multiple d-branes, for example, right, how it acts on the d-branes, right? It may take open string going from d-brane 1 to 2 and map it to open string going from d-brane 2 to 1 and so on. So that something that you have to specify. And the idea is that you project out, you take the quotient by this transformation, take the quotient of the theory by this transformation. Okay, which means you restrict to closed string states which are invariant under this transformation. You have closed and open string states which are invariant under this transformation. Okay. And as we saw in the case of bosonic string theory, the effect of this is to exchange the left and right moving modes. Okay. So this exchanges, for example, alpha tilde mu n to alpha mu n to alpha tilde mu n, bn to b tilde n, cn to c tilde n. Okay. So this was for the bosonic string, but now you also have psi mu r to psi tilde mu r, beta r to beta tilde r, gamma r to gamma tilde r. And then for picture number e to the q phi goes to the q phi tilde, etc. Okay. And the other important point that we had for the bosonic string is that it takes 0 to minus 0. Okay, this is needed for consistency. Okay. Otherwise, the gravitons will be projected out from this. Okay, and that we can show is not a consistent theory. So it takes 0 to minus 0. Okay, so we'll discuss some examples of states. Now, one point before I go on, that because it exchanges the left and right moving sector on the world sheet, okay, that this can be done only for type 2 P. Only for 2B.
Why did 0 and 2 minus?
Yeah, I'll explain. Okay. So this can be done only for 2B, okay, because 2B has the property that the left and right moving spin fields have the same chirality. Okay, so it makes sense to exchange them. Right? You cannot exchange fields of opposite chirality. Okay. So for 2A, there is a more general kind of possibility, okay, which of course exists also for 2B. Okay. So let's take 2A. Right? Suppose you have to do something similar for 2A, right, where the left and right moving modes have opposite chirality. Okay. What you can do is that you accompany omega by a parity transformation, by say x9 goes to minus x9. Okay. Under parity transformation, the chirality changes.
Target space parity.
Target space parity. X9 goes to minus x9, for example. Right? Because under parity transformation, the left moving spinner, a dotted spinner goes to undotted spinner and vice versa.
Under parity, this happens.
Under parity, yeah. No, that is the world sheet parity. I'm talking about space-time parity. X9 goes to minus x9.
Yeah, so I think gamma matrices really.
Exactly. Gamma matrices will relabel. If one gamma matrix changes sign, right, then basically dotted spinners become undotted spinner and vice versa. Right? So if you have a left moving dotted and right moving undotted, right, then under parity, the left moving dotted will go to right moving, left moving undotted will go to right moving dotted, because you are doing a simultaneous transformation. You are first exchanging left and right on the world sheet and making a parity transformation in space time. Okay, so this is possible, right? So for type 2B, if you want to do this for type 2A, right, you have a possibility of reversing either one of the coordinates x9 to minus x9, or three of the coordinates x7, x8, x9 to minus x7, x8, x8, x9, etc. And for 2B, you can do it for even by using even number of coordinates whose sign you change. Okay, but this is the simplest case. Okay, where you have not done any world sheet, any transformation on the target space. You are just going using omega.
Like if I take this psi to minus psi, so that will just change like
Yeah, if you take one of the sides to minus psi, they will get exchanged.
Plus minus will probably become minus plus.
Exactly.
That makes the spinner.
Yeah, so one of the plus minus will become minus plus, right? And that changes the chirality of the spinner.
Yeah. And they'll have to do it consistently with, like, if I take x to minus x, then the corresponding side has to be.
Exactly. Yeah. Okay, but those will break Lorentz invariance, right? Those will not have 9 plus 1 dimensional Lorentz invariance because x9 goes to minus x9 doesn't commute to the Lorentz group. Right? So if you want a full 9 plus 1 dimensional Lorentz invariance, this is the only possibility. This type to be. Okay. So let's look at the spectrum, massless spectrum, massless bosonic spectrum. You can also do the fermionic spectrum. Okay, well, let's look at the massless bosonic spectrum. So NS will be of the form zeta mu nu C1 tilde psi mu minus half psi tilde nu minus half e to the minus phi by 2 e to the minus phi tilde by 2, sorry, e to the minus phi e to the minus phi tilde on the vacuum. Okay, here I have written down the full massless sector in the original theory. But let's see what omega invariance means. So omega changes C1 and C1 tilde, right? So that's a minus sign. You can bring it back with a minus sign. It changes the positions of these. Again, you can bring it back with a minus sign. Okay? And it changes the positions of these. Right? These are also Grassmann odd variables, so you can exchange and put a minus sign. So you get 3 minus signs, right? So it will get a minus sign, overall minus sign. If 0 also has a minus sign, right, then it comes to the plus sign. Okay? Except that this mu and nu had gotten exchanged, right? Okay? So zeta mu nu should be equal to zeta nu mu for omega invariance. So B field is gone. Okay, graviton and dilaton survive, but B field is gone. If the vacuum didn't change sign, right, then it will be the other way. Right? B field will be there, but graviton and dilaton will be gone. Right? And that one can show it's not a consistent theory at the end. Right? When interactions will start producing the gravitons which you had projected out.
So you want also vacuum to have.
Yeah.
So this is like, if we want graviton and dilaton, 0 must be.
Yeah, that's right. But you can also show that now once you include interactions, right, then you can't get the other one, right? You can assign another transformation loss of vacuum.
Like there cannot be just a B field theory.
Yeah, because 2 B's will produce a G, right? In the vortex, there is an interaction vortex where a single metric couples to a pair of B's. Right? If you assign that a metric has odd sign under this and B has even sign, then that vortex is odd, right?
So it cannot be like is this same as saying that it cannot be simply a topological term that describes the interactions? Like metric has to be involved somehow.
Yeah, we know the original theory had a metric, right? So if the original theory had a metric, then there is a process where 2 B's gonna collide and produce a metric. Okay? So from the space-time viewpoint, it's clear. See this symmetry by which you are quotienting better be the action of the better be a symmetry of the original theory, right? Okay? The original theory had a coupling where a metric couples to 2 B's, right? So changing the sign of the metric and keeping the B's unchanged is not a symmetry of the original action, right? which basically means that in the interacting theory, this is not the only consistent way that you can implement this symmetry is by declaring that this is odd.
But like, what I'm asking is like, say I forget about the original action. I have this new theory at the worldsheet level.
Yeah, but at the worldsheet level, right, 3-point function between a graviton and two B's is non-zero.
Yeah, but I would probably want to even consider that once I have projected out.
No, you have to check that the ones that are projected out actually decouple. Yeah, exactly, it will not be zero. Because it's the same calculation, right? One graviton, two B's.
But if we define like at the level of Polyakov action,
Yes.
We don't have a metric, we just define.
At the level of, see, the Polyakov action in the worldsheet, right? I'm saying from the target space viewpoint, right? The 3-point function, you have to make sure that the whatever projection rules you give, right, when you apply on the vertex operator, right? The vertex operator of 1 odd and 2 even fields will automatically be 0. Right? Otherwise, they are in trouble, right? Because 2 odd even fields can produce an odd field. Okay. If we declare that the metric is odd and the B is even, right? Then then two B's shouldn't be able to produce a metric, right? But the worldsheet is the same, right? Sphere you have to include. Is this clear? Right? So this argument was there even in the case of Bosonic string, if you remember, right? That you have to include, you have to do this. So you have to use the symmetric one. RR, let's say, so this is zeta xi, let me call this something else, xi AB, C1 tilde, yes, tilde. So if you now apply the worldsheet parity, C1 and C1 tilde will get exchanged to the minus sign, right? You have to bring it back, it's a minus sign. These two will get exchanged, but again, we have to bring it back with a minus sign because these are Grassmann odd variables, right? These are Fermionic objects, and 0 has a minus sign. 0 is the same vacuum, right? I'm not using RR vacuum because these things create the RR states out of the vacuum.
Change SA to S tilde.
Yes, right? Omega will change SA to S tilde, right? And phi to phi tilde. Okay, but so there is a change of order here, you bring it back. There is a change of order here, you bring it back, and the change of and the minus sign here, right? So 3 minus signs gives you -1, right? So then xi AB should be equal to minus xi BA. Is clear? Okay. Now, if you remember, in the Ramon sector, these vertex operators in a minus of picture are creating the field strengths. Okay. Originally, we had a bispinner, xi AB, without any symmetry restriction, and that produced the field strength of the type 2B theory, right? Which means the one form, that is the D of the axial, the Ramon scalar, 3 form, that is the D of the 2 form, right? And then a 5 form, that is the D of the 4 form. Okay. One can check that once you impose this restriction, this is a group theory problem, that then the DC0 and DC4 are absent. Only DC2 is there. Is clear? Okay, another way of saying this is that if you look at the combination, yeah. So so the point is, idea is that you shouldn't do separate them out, right? You take this whole e to the minus 5/2 SA, right? This creates a space-time fermion from a bosonic state, right? So this is has to be treated as Grassmann order, right? You just exchange the whole thing together. Okay, so the equivalently, basically what we are saying is that if you take gamma mu1 to mu t mu k AB, this is the way you construct the field strengths, right? Contracting this gamma with xi AB.
Why e to the minus 5/2 SA? We should consider the worldsheet Grassmann parity.
But also the space-time Grassmann parity. Because otherwise, how will you get recover spin statistics? Right? So once you know that something creates a space-time fermion, you have to assign odd Grassmann parity to that combination. Yeah, otherwise in the interaction, right? Suppose you're calculating the 4-point function, right? You exchange two of these. Okay, you should get a minus sign. Right? That will have to come from the worldsheet.
So I have to consider both.
You have to consider both. So that something is Grassmann odd or Grassmann even is controlled both by the worldsheet Grassmann parity as well as the space-time Grassmann parity. Okay, so the claim is that this is odd only for k equal to 3. Right? For k equal to 1 and 5, this is even. Okay? And that's why this is projected out, because you have to contract with something which is antisymmetric. Or maybe I should say not antisymmetric. Under A goes to B. Okay, so this basically means that C2 survives. So while it is true that the NSNS2 form is gone, okay, the RR2 form is present. Is clear?
Is this easy to see?
What is easy to see? Well, no, it's not probably very easy to see. You have to just look at the properties of the gamma matrix. I mean, okay, this means transpose, right? You have to check what happens to this under transpose, right? So you transpose all the, you write it as gamma mu k to mu gamma mu1. Then you have to take, commute them together, right? Then you have to see how the transpose relates to the original gamma matrices. Right? So it's not hard, but you have to do it, just do a little work to see this.
But probably for like k not equal to 3, it may not even have a nice property.
No, it always has a nice property.
Like it will
Even
be
or odd,
only
yeah.
for X.
Exactly, yeah.
So
It will be,
for other cases, it's this.
exactly, yeah. You can see that it will have a nice property because if you take the transpose, right, basically you, these come in opposite order, right? And each of them get transposed. And you just rewrite this in terms of the original gamma matrix in the same order. Okay, so this is about the spectrum. What about interactions? We need a new worldsheet. Which are unoriented. So the first one that contributes, okay, is what is called RP2. This is a leading unoriented worldsheet. So RP2 is leading unoriented worldsheet. Okay. And it is obtained by appropriate quotient of a sphere, right? Sphere or a complex plane. Okay, I'll explain what that quotient is.
For oriented worldsheets, the contribution is calibrated by the genus.
Yes.
Here, there's no concept of genus.
No, there is no concept of genus, but you take the original genus that you are quotienting and divide by half, right? So it's a Z2 quotient, right? So you still have a contribution. It's the analog of the genus, right? But you define it appropriately for this. Okay, I'll describe a way to count what the factor will be, the effective genus. That's how you count.
Like it will be always like this RP2 is obtained by sphere you quotient by.
Yes, I mean,
A2, but I take torus, I'll get something you're saying.
you'll get something else, but we will see how to describe the torus in this language. How do they describe the quotient of the torus? So the one way to describe this is that you take the complex plane. So you have to divide by something that changes orientation, right? So z goes to a function of z is not going to change orientation, right? So the complex plane, you have to change one of the directions, right? So z goes to z bar changes orientation, right? Because z goes to z bar is you are changing the coordinate of one of the coordinates, right? If you write z equal to sigma plus I tau or x plus iy, you are changing one of the coordinates. Okay. But z goes to z bar is not a good idea, right? Because that transformation has a fixed point, right? Fixed point means what? That there are points in the complex plane which are invariant under such transformations, right? Z goes to z bar, the whole of real axis will be fixed, right? So it will produce a singular space. So you have to look for a transformation that produces non-singular space, which means no point on the complex plane should be invariant under that transformation. Is this clear? Right? Because whenever you are quotienting, if there is a fixed point, then it produces a singular space-time, singular worldsheet. You don't want singular worldsheet. Okay? So here I'll tell you one way to get this, okay? And that is to take z goes to minus 1 over z bar. Z goes to minus 1 over z doesn't change orientation, right? That's just a conformal transformation. Right? So it's a composition of a conformal transformation z to minus 1 over z and then z to z bar. Okay, that changes orientation. Conformal transformation doesn't change orientation. Now, why is it free from fixed point? You can see because fixed point will mean that these two should be equal, right? Z equal to minus 1 over z bar. That gives you z bar equal to minus 1. But there's no point in the complex plane for a z bar equal to minus 1, right? So that's why it acts without fixed point. But this is of course not the only way to get it, right? Because once you have gotten it this way, you can make any SL2R transformation of conjugation of this and you can still get or any SL2C conjugation of this and you can still get another representation of RP2. Okay, but this is good enough for us.
This is the same as taking the Riemann square and doing anti.
Exactly, yeah, because this is basically doing the antipodal. I mean, if you use the stereographic projection, okay, this is essentially doing the antipodal identification. Okay. So this then can be represented as a unit disk because any point outside the unit disk can be mapped to a point inside the unit disk by using this map. Is clear? Right? So points outside get mapped to points inside. So let's see what happens on the disk, on the boundary. Points inside the disk will go outside, right? So that's why it's enough to restrict to this region, right? Anything outside will go outside anyway. on the boundary is z equal to e to the I sigma, right? So this sends sigma to sigma plus pi. Is clear? So we identify antipodal points. Yeah, you can see if you do this stereographic projection, right? Then the boundary, the unit circle is the place where the plane cuts the sphere, right? And there the antipodal mapping will go to precisely sigma goes to sigma plus pi. Is clear? So this also shows that there's no fixed point, right? Points outside go to points inside, and points on the boundary actually get translated by pi. So nothing remains fixed under this Z transformation. So it's a perfectly smooth unoriented spacetime, or unoriented Riemann surface. Is this clear? Now you may recognize that this is very much like a unit disk that we were doing for D branes. Right? For D branes, we can calculate the correlation function either in the upper half plane or unit disk, right? They are equivalent. Okay. So this is as if you have something like a disk, except that on this boundary you don't put Dirichlet boundary condition on the fields. Instead, you put periodicity, antipodal map. Right? The field here should be equal to the field here. Right? Maybe with some minus sign, because that depends on how the conjugation acts on this transformation.
We looked at this thing and we said after this mapping, points inside will go outside.
Yes.
Points on the surface will stay.
Exactly. Right. So that means we can represent the Riemann surface, okay, just in terms of the interior with these points identified. So the exterior points can be brought inside anyway, right?
So your theory is like omega.
Exactly. Because you are not just omega invariant, you are doing omega quotient, right? Omega quotient meaning you identify states under omega. Right? So that's the reason why you just can describe the Riemann surface by this, by a disk. Right? So this is like a unit disk with Dirichlet boundary condition, except the Dirichlet boundary condition has been replaced by this kind of periodic boundary condition. Okay? So this is what is called crosscap.
But why? I would think that we needed sigma goes to minus sigma somehow.
Yeah, so this is effectively sigma goes to minus sigma accompanied by a conformal transformation. Right? Conformal transformation in any case is a symmetry. Right? You are just combining a conformal transformation, sigma goes to minus sigma.
This crosscap is RP2.
Yeah, this is called RP2. Okay. And so you have to, when you calculate sum over Riemann surfaces, you have to sum over also this Riemann surface. Okay, which looks like a disk, but it's not a disk. No, the unoriented, the oriented surfaces also are there. Right? Sphere is always there, torus is always there. On top of that, you have to do this crosscap, right? And we'll have to do more that we'll see. Is this clear?
This point I didn't completely understand.
Why sphere is to be included?
Yeah, the other are there.
Yeah. See, maybe we'll discuss this.
But
Problem.
maybe it's that which people.
Yeah. See, sphere in. I mean, what do you have to do here? That once you impose this quotient, right? Then anytime you cut a line, you have to put a projection operator, because you only want the invariant sets to propagate, right? Okay. Let's take a loop, right? Along the loop, see, if you cut a tree, right? Then it should be automatic. Right? Take a sphere is 4 function, and you cut into 2-3 point function, right? Then as long as these are invariant under omega, it's guaranteed that this will also be invariant under omega. Right? In a loop, it's not guaranteed. Right? Imagine a sphere with 3 punctures, and you join 2 punctures by a handle. Right? So then there you can have sum over all states, right? Both omega invariant as well as omega odd, right? Because a pair of omega odd states is what you're considering. So there you have to put this condition explicitly, right? That there is a projection. Okay? So there is a trace of 1 plus omega by 2. Right? The one part is the original Riemann surface, right? The omega part is producing the new Riemann surface, right? Because you are twisting and gluing, right? You are doing a Walsh parity transformation before joining the handle. Okay? So it's the omega part that requires unoriented Riemann surfaces. Okay, and that's what we are using here. Is this clear? So here, okay, so now let's look at the symmetries of this crosscap. Okay, whether SL2 are clearly, sorry, SL2C clearly is not a symmetry of the crosscap. Okay, because you have chosen the Z goes to -1 over Z bar doesn't commute with the full SL2C transformation. Okay. But there is a subgroup of SL2C that does commute with this. You can probably recognize it by looking at the picture. Right? What subgroup will commute with this? That's basically rotation. It's because it's the same, it looks like a disk, right? Unit disk. On a unit disk, we say there's a conformal killing vector that's left over, there's a rotation, right? This is also the same. Right? This will be invariant at rotation, but that's a compact group, right? So you can divide. Okay? So just like on the disk, right? The C0 minus C1 bar, right? That was the vertex operator that you have to use to calculate a one-point function. Right? For crosscap is the same, right? You put a vertex operator here and then you use C0 minus C1 bar. On VR equivalently, you can write as half del C minus del bar C bar C bar B. Okay, very much like what you did for the disk.
It's so the point was that this identification commutes with the rotation.
Exactly. This identification commutes with the rotation. Okay, and the procedure for calculating correlation function on this disk is also clear. Right? Imagine that you have a certain set of operators inside on the disk, right? How do you calculate the correlation function? You just place the images on the outside, because this was obtained by taking the omega quotient of the original Riemann surface, right? To calculate the correlation function of a set of operators here, you put the images on the outside, right? And then calculate the correlation function on the sphere. Just like for D-branes, we used image, right? On the we reflected around the real axis. I should have said I can also represent this as a quotient, this boundary. I can map it to the real axis, right? It's just the rotation will look somewhat different. Right? But you can, once you have gotten this, you can always make an SL2R conjugate that maps the boundary to the real axis. Right? So I could have used that representation also, but in this case, it's easier to look at in this picture. Right? So calculate a correlation function on the disk. You just place the images outside and calculate correlation function on the sphere. Right? So 3 C's inserted here, okay, will produce 3 C tilde outside, right? Because Z is going to -1 over Z bar. Okay, you put 3 C tildes and then calculate the corresponding correlation function on the sphere.
But one thing is, like, for this, we sort of had this in mind that we have a D-brane and a boundary renting there. But
Yes.
here there is nothing like that.
There's no boundary. Exactly.
Yeah, it doesn't necessarily require an object in the space-time.
No, it doesn't require an object in the space-time. But this, you can think of this as an object. It sometimes referred to as Orientifold plane.
Orientifold
Plane. Right? It's as if you have created an object by this quotienting. But it's not a dynamical object. You cannot just move it by quotienting. Right? Yeah, because you will see that this acts as a source of fields. Right? Here, for example, the one-point function, the same reasoning, the one-point function is not 0. Right? So one-point function of the graviton and the Raman fields and the dilaton are non-zero. Right? Because the one-point function, you can place this vertex operator, place its image and do the calculation, right? In general, there is no reason why it should vanish. Okay. So it will have exactly the same kind of problem that we had here for D branes. Sorry, this is how we raise that, right? For D branes, we had the one-point function, right? And then the massless particle, right, connecting two one-point functions gave rise to divergence. Right? Same divergence will appear in the presence of a crosscap Orientifold plane.
But can I talk about like mass of such a thing or?
Yeah, you can talk about the tension of such a thing because you calculate the one-point function of the graviton, right? That will give the tension of this thing, right? Except the tension in this case is negative. Okay, this comes out negative, but you can calculate it.
Since these are not dynamical, how do you see that?
That if you had done, in this case it's hard to see, right? This whole space filling anyway, so dynamical, it's not clear what it means. But D-branes, for example, if you have D-brane localized in some subspace, right? You know that it's dynamical because there are massless modes which allow you to move in the transverse direction, right? Here, if you do similar Orientifold plane, right? Not space filling, right? But imagine that you reflect around, say, P of the directions, right? Then there will be P transverse directions, right? Because it has to be located at the x equal to 0. Okay? Then there will be no massless states, extra massless states that will get, which will allow it to move. Right? So in that sense, it's not dynamical. It's basically located at a fixed point, fixed plane.
No mass that I can see by saying that this projection, like massless states don't survive.
Exactly. So we have the massless, there are massless closed string states, right? Some of which survive, but those are just bulk states. Right?
Like
you don't get extra states that allow you to move this in the transverse direction. Unlike for D-branes.
But those are open string states.
For D-branes, it has open string states. Here, of course, there's no open string state, right? Here, it's only basically you are looking at the closed strings. You can put D-brane on top of it, right? But then those modes will be the modes of the D-brane, right? Not of the crosscap, not of this Orientifold.
They are just the spectrum is whatever you have written.
Yeah, yeah.
You are saying that it doesn't have any massless.
Extra massless modes, yeah.
Extra massless modes corresponding to
Moving the crosscap.
translation.
Exactly. Translation in the transverse direction. No, there is no, because for in the present of Orientifold plane, you just project, right? You don't add extra things.
Like for D-brane, it was like probably del X, something like that.
Yeah, exactly.
C del X.
Yeah, C del X, right? Here there is no an extra field that you introduce.
Is this type 0? This thing is.
No, this is type 1. Well, yeah. We will see, I mean, it is not type 1 yet. We'll see how to make it type 1, right? So this is just the ingredient that you can take a cross cap and get a non-zero result. So in the language of so now I mean earlier we had a one-point function, right? Let's call this a D-brane one-point function. These are due to the D-brane, right? Okay, now we have a new object, right? Which is a one-point function of fields, but because of the Orientifold, right? So let's call this a cross-cap one-point function. The effect of this is the same. You will get divergences, right? Because if you now calculate two cross caps, this is divergent. So if you can calculate the contribution from this divergent, the coefficient of the divergence, right? The same way we did earlier, integral ds, right? The coefficient of s. Then using that, you can calculate how much is the one-point function, right? Just like we did for D-branes. Is this clear?
But one point we know already.
Again, the normalization you don't know. The ratios of one-point function you can calculate, right? The normalization you don't know. Right? So for normalization, you have to do this calculation. Right? This is what is called Klein bottle. The worldsheet picture is this. You take a cylinder, but here you put a cross cap and a cross cap. So there's a boundary here, right? Okay, both are cross cap. This is Klein bottle. And the result is okay. So now, how do you calculate this? The way you calculate this is that this is coming because of this. We have trace of e to the minus p times L0 plus L0 bar. This is a closed string. Okay, and then you have again B some B0, C0, B0 bar, C0 bar for the zero modes. And because of this Orientifold projection, you have to put a 1 plus omega by 2. This contribution, 1, is a torus contribution because you're taking a closed string state and identifying, right? Let me do it to make connection with the other one, right? Let me draw it this way. Okay. You propagate and then you identify these two. So this is the original torus contribution, except that you have a factor of half. This one is a Klein bottle, the omega part. Okay. So if you know the spectrum, right, you can actually evaluate this. Right, because you know how omega acts on various closed string states, right? The massless, massive, everything, right? Because you have given the rules of what omega does. Okay. You can evaluate this. Okay. And then you have to be a little more careful to convert to S. So you have integral dt over t to t of this, right? And then you have to convert it to integral S, where S is basically a dual variable. You have to look at it now on the dual channel, right? Where you have to, we can think of this as a closed string exchange between two cross caps, right? So it's a question of whether you're thinking of this, whether you're looking at the propagation in this direction or in this direction, right? You can think of this as a closed string exchange between two cross caps, right? That's the variable S. Okay. So you have to work out the relation between T and S, okay, by following similar procedure. Okay. And this tells you this can be used to compute normalization of a one-point function.
Some of this one will give you the like single completed course in brain.
Pardon?
This one plus omega. The one part will give you something similar.
No, something similar, but in a closed string channel, right? This calculation is done purely on the closed string sector. Okay, so you do something similar to what you did for open strings, right? Using t variable, you are using the same t variable, right? And then you have to re-express this in terms of the 1 over t variable, right? Which is the S. Okay, you have to work out the relation between S and t by looking at the geometry, okay? And that gives you the integral ds times something and that coefficient, right? Which you can read out. You compare with what you will get from a Green's function calculation, right? Imagine that you have a source, that calculation is identical, right? Except that this, instead of T, you will have a TC, right? The tension of the cross cap.
So the difference is in the dt S was over open string.
Yes,
It's closed string. In the S channel also it's closed string.
exactly. Yeah, in the S channel also it's closed. Okay. In fact, there's a simpler calculation you can do. Closed strings are a little harder because you have both L0 and L0 tilde, which is the cross cap, this diagram. So in the worldsheet language, this is like this. One end is a cross cap, the other end is D. Okay, this is D brane. So this will be proportional, this gives you TC square, right? This gives you TC square. This one is basically coming from trace of open e to the minus TL0, then again B0, C0, 1 plus omega by 2. The omega by 2 part. Right? That's what is producing this. Okay. Geometrically, this is the Mobius strip.
One thing I didn't understand is like there 1 plus omega by 2 you inserted and you have like both cross cap and a torus spectrum.
Yes, the torus is the one and the cross cap is omega.
Yeah, yeah. But this represents that diagram.
Yeah. This represents this diagram.
That the one cross cap or
No, what you can show is that, I mean, if you, because you go around the closed string, right? And you basically need two of them
okay.
to get a 1 plus omega by 2.
But still, I mean, then why is there a torus?
Why torus?
Like if omega is
I mean, one way to do this is to do genus counting, right? So basically what happens is that the genus counting is such that the cross cap, right, gives the same kind of genus counting as a normal boundary. Right? It basically adds a GS factor. Okay, so take the sphere, right? Sphere has 1 over GS square, right? Every time you add a boundary, you get an extra factor of GS, right? That's why the annulus has GS to the 0, right? Because it's like a sphere with two boundaries. Same is true for cross cap. Okay, every time you add a cross cap, you get a GS, right? The torus is GS to the 0, right? So if this one is GS to the 0, it better be that this omega also gives GS to the 0.
like my question is like why is there even a 1 in first place? 1 by 2. Why is there like if I'm just saying that the dual thing I know it's a closed string propagating between two cross caps.
Yeah, but the one loop partition function of the sphere of the closed string should have this, right? See, 2 cross cap is genus 0. That we agree, right? From this counting. So we need some genus 0 contribution. Sorry. Yeah, not genus 0. Genus 2. Yeah. Genus 2 contribution. Right? So this torus is genus 2. Sorry, not genus 2, genus 1. GS to the 0, right? So torus is GS to the 0.
Yeah.
Right? And that is trace of this 1, right? When you have 1 plus omega by 2, we need a GS to the 0 contribution. Right? This has no coupling constant anywhere. Okay. Right? So you need a GS to the 0 contribution, and a GS to the 0 contribution requires 2 cross caps. Because take a sphere, right, which has 1 over GS square. Every time you add a cross cap, you get a GS. Right? So 2 cross caps will produce GS square. Right? That's the reason why this is the Klein bottle. But to calculate TC, right, it may be easier to do it this way. Right? Here it's D9 on one end and then a cross cap on the other end. Okay. Once the space-time interpretation is it's this combination. Okay. And from the open string calculation, the way you will do it is that you will basically pick up the omega contribution, right? You have already seen earlier how to do the one contribution, right? Omega is similar, right? Because you just have to calculate the partition function with an omega inside. Okay? And follow the same procedure that we followed earlier. Okay? Convert from the t variable to s variable. Okay? And that determines the product of TC and TD, TC and T9, right? So this gives you T times TC. This gives you T times TC. T is the deep-band tension, TC is the cross-cap tension or the Orientifold tension. This one gives you TC square. And the cylinder gave you T square, right? And you can check that these are all compatible, all consistent with each other, right? Because once you determine T and TC, then T times TC is automatic. So the sum of these is basically T plus TC square is proportional to T plus TC square. And in order to get a consistent theory, we need T plus TC to be 0. Yes, all these three. Because one gives you T square, one gives you TC square. Other one gives you in fact 2 times T times TC because you can exchange these two, right? So recall that T plus TC square multiplies this divergent integral, right? Integral ds. Okay. So if you want a sensible theory, it better be that T plus TC is 0. Okay. Physically, it's clear what it means, right? Physically, what it means is that there should be no one-point function at the end. That this plus this should be 0. Okay, this is proportional to TC, this is proportional to T. Okay. And the result that one finds is that we need 32 D9 branes.
Crosscap 1 point vertex plus equivalent 1 point vertex equivalent.
Yeah, but if you put n D branes, right, then this is n times this. Because each vertex gives you some contribution, right? N D branes will give you n times T. Okay, let me call it n, right, for n D branes. N D9 branes.
How is that related to this T plus TC being 0?
Yeah, so by T, I am now meaning n times T, because if there is n D brane, T is replaced by n times T. Right? So I can say n T plus TC equal to 0.
But why did I want it? Why would I want T plus TC to be 0?
N T plus TC equal to 0, because you can see from here that 1 point function you want to vanish, right? We said that if you have a 1 point function of a 10 form field, equation of motion cannot be satisfied, right?
Yeah.
Because delta C of that is a constant, right? We also saw that you will get various divergences, right? These diagrams will be divergent. These have like integral ds, right? So these are divergent diagrams. Thus that coefficient is also same, proportional to nt plus tc, right? Because basically it's 1 point function squared multiplied by 1 over 0, right? So the net 1 point function should vanish. That's the condition, right? And that from that everything else follows.
But we didn't require anything like this, like for the only D-brane case. What was the analog of that?
So for if you just have just space filling D9 brane,
Yeah.
then it's not a consistent background. We calculate tension, right? But the back reaction will make the theory inconsistent, right? Because you cannot have non-zero one-point function. So that calculation was just to see what the one-point function is, right? It's only when you cancel that one-point function with something else that you can get a consistent theory.
And this is one way to.
This is the only known way to do this, right? If you have a space-filling brane,
You should have a crosscap.
you have a crosscap, Orientifold. Okay. And basically what happens is that in this case, if you have 32 D9 branes, there is a U32 gauge group. Okay. Except that not all the open strings on the D9 brane are survived, right? Because you have to also have the omega projection. Okay. So when you quotient by omega, no, to begin with it is U32. If you have n D9 branes, the gauge group is UN, right? But once you do the quotient by omega, okay, it becomes SO32. Okay, because SO32 is a subgroup of U32, right? But many of the open strings get projected out, and you end up with SO32 gauge group. So this is what is called type 1 theory.
So if we do the trivial this TC calculation,
Hmm.
it will come out to be some 32
Exactly.
minus
32, yeah. The TC calculation will come out to minus 32 times T, right? That's why you need n equal to 32 to exactly cancel the charge. Yeah, then you are in bad luck, right? Then you cannot get a consistent theory. So you are lucky that you got some integer.
So, I mean, this T plus TC being 0, we need it for the
Consistency, yeah.
for the space.
For space filling, yeah.
Space filling.
Exactly, yeah. For non-space filling branes, there is a problem, right? Because the flux can leak out, right? We can have electric charge. Okay, space filling, or let me say if you have compactified theory, right? Then if it fills the non-compact space time, then also you need this. Imagine you have a circle, you have a D8 brane and there is a transverse circle, right? Then also you have the problem, right? Because flux cannot leak out.
Okay. Oh, you need a non-compact direction.
To allow the flux to go. Yeah. Right? A point charge in 3 dimensions has no such problem. But if a 3 space directions was compact, say on a torus or in a sphere, then you have problem, right? Then you can have a single point charge. You have to cancel it.
Can you just remind me why C2 survives? Why was that important? Or like, what's the significance of that?
Well, the significance of that is the type 1 theory when you look at the spectrum, right? It will have a SO32 gauge field, right? It will have a graviton, dilaton, the massless spectrum, and the 2 form. Okay, and this theory is supposed to be dual to SO32 heterotic theory, which has exactly the same spectrum, right? But there the 2 form comes from the NSNS. I mean, there in fact there is no, RR sector is not there, right? Because in the heterotic theory, you have only NS and R, right? So all the bosonic states come from the NS sector, right? But these 2 theories are supposed to be non-perturbative dual. So they are supposed to describe the same physical theory, even though they look very different, right? Here the gauge fields come from open strings, right? Whereas in the heterotic theory, there are no open strings, right? Everything comes from closed strings. Okay, I think that's it. Any question? What? You look very surprised or no? What? Photo? Yeah, you can have photo. Yeah. So that's exactly what once the charges cancel, right? And the cosmological constant cancel.
The tension has to cancel TC.
Exactly. Right? So the Orientifold has opposite negative tension. Right? That's another way to see that it's not dynamical, right? You can have a negative tension object that moves. Right?
In heterotic
Heterotic, is there a particular background it should map to, or just simple flat space?
The flat space background, yeah. Because here, because once the tensions cancel, right, then the flat space is a solution.
Okay. Yeah.
There's no back reaction, right? ADS-CFT hasn't come here. This is perturbative string theory. If you put lots of D branes, not D9 branes, you have to put D3 branes, right? Because space filling brane, you cannot have charge, right? But as Rishabh was saying, that if you have D3 branes, you can put lots of D3 branes, right? And then you can look to study its back reaction. There, the near horizon geometry becomes. But T is the source, right? Then you have to look at what the source produces, what geometry the source produces, right? And the near horizon geometry of the D3, a stack of large number of D3 branes is ADS5 times S5.
But there I don't want any vanishing of the tension.
No, because it's not space filling.
Not space.
Yeah, because it's not space filling.
No, then you had the geometry. Okay, you stack up D branes.
Yeah.
Near horizon, you have the geometry.
Yeah. So now the point is the near horizon, you have two ways to look at the near horizon geometry, right? Near horizon, because of the high redshift, right? They are very low energy excitations near the horizon, right? So you can think of either as low energy excitations of gravity, ADS5 times S5, right? Take any string state, go near the horizon, it will look like it's almost massless, right? Okay, so that's one way of describing this, right? The other way is just think of this as a stack of D3 branes, and the low energy dynamics is described by UN Young-Mills, super Young-Mills, right? And
Low energy gravity excitations are like that of what?
yeah,
Case theory.
exactly. So the point is the low energy, not just gravity, low energy string theory excitation, because the whole string, see, it's not just the gravitons which become low energy, even heavy string state, right? When you go to near the horizon, due to redshift, it will look like a very light state, right? So when you are looking from infinity, right, there are these two ways of looking at light states, right? One is that it's as if it's the full string theory in the near horizon geometry, which is ADS5 times S5. Right? Other one is that you think of this as stack of D3 branes, right?
Like some Q and case.
Yeah, and the low energy dynamics of that is just a even gauge theory, right? And that's the duality. That was the original motivation as to for ADS-CFT. That so because there are two different low energy descriptions of the system looked at from far, right? There should be some equivalence between these two descriptions.
It's only happened for this one particular years.
Yeah, because near horizon geometry, I mean, okay, there are other examples, right? In M theory, for example, there are these ADS4 times S7 and ADS5, 7 times S4. So those geometries are there. But it's like always like this, that you think of this as a system of branes.
You get some near horizon ADS and then some case theory.
Exactly. Yeah. Or if you just all stand in front of the camera, they will automatically come, right?